Hello there and welcome back to the Science Sleepy Minds. Tonight, you're standing on the edge of something extraordinary. Picture yourself barefoot on a hillside, the grass cool and slightly damp beneath your feet. The sky above you so clear that every star looks close enough to touch. And there, low on the southern horizon, burning with a steady amber glow, sits a star you have probably glanced 1,000 times without realizing what it truly is. Alpha Centauri. The nearest star system to our own. Just 4.3 light-years away, which sounds like a gentle stroll in cosmic terms until you remember that a single light-year is roughly 6 trillion miles. So, pack a lunch. You probably will not survive this journey in any literal sense, but your imagination is about to do all the heavy lifting tonight. And honestly, it is better equipped for the trip than any spacecraft we have ever built. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you are at it, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone is always tuning in at 3 in the morning from somewhere unexpected, and that energy is exactly what this channel is about. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle back, and the hillside seems to tilt gently, as though the whole Earth is angling itself to give you a better view. Because something happened recently that changed the way scientists think about that amber dot in the sky. The James Webb Space Telescope, humanity's most powerful eye in the heavens, turned its enormous gold-plated mirror toward Alpha Centauri, and what it found there sent a quiet shockwave through the global astronomy community. Not the dramatic, headline-screaming kind of shockwave, more like the slow, breathless realization that the universe next door might be far more interesting than anyone had dared to assume. To understand why this matters, you need to appreciate just how personal Alpha Centauri feels to astronomers. This is not some abstract quasar billions of light-years away. This is the porch light of the nearest house on the cosmic block. Humans have been staring at it for thousands of years. Ancient Australian Aboriginal astronomers, whose traditions represent some of the oldest continuous cultures on the planet, incorporated Alpha Centauri into their oral star maps and seasonal calendars long before any European ever pointed a telescope at the sky. They understood that certain stars mattered not just for navigation, but for timing the cycles of the natural world. And Alpha Centauri, bright and reliable, was one of their favourites. Historians still argue whether early Polynesian navigators also used it as a key waypoint during their extraordinary open ocean voyages across the Pacific, though the evidence leans tantalisingly in favour of yes. There is a quirky footnote here that most people never hear about. In the 1950s, a small but enthusiastic group of radio astronomers briefly convinced themselves that they had detected an artificial signal coming from the direction of Alpha Centauri. It turned out to be terrestrial interference, probably a taxicab dispatcher in Sydney, which is both hilarious and a little bit heartbreaking. But for a few giddy hours, a handful of scientists genuinely wondered if somebody next door was saying hello. Now fast forward to the 21st century, and the James Webb Space Telescope is floating at a point in space called L2, about 1 million miles from Earth, on the side opposite the Sun. Its sun shield is deployed, its instruments are cooled to temperatures that would make a penguin file a complaint, and it is staring into the cosmos with a 6.5-metre primary mirror made of 18 hexagonal segments, coated in a layer of gold so thin you could not feel it between your fingers. This telescope was not originally designed with Alpha Centauri at the top of its to-do list. Webb was built to look deep, to peer at the earliest galaxies forming after the Big Bang, to study the atmospheres of distant exoplanets, orbiting stars hundreds of light-years away. Pointing it at something as close as Alpha Centauri felt, to some in the astronomical community, almost like using a Formula One car to drive to the corner store. Technically impressive, but perhaps a little over-engineered for the errand. And yet, when the decision was made and the telescope began collecting photons from our nearest stellar neighbour, the data that came back was anything but mundane. You're going to spend the rest of tonight learning exactly what Webb saw, why it matters, and why some of the smartest people on this planet are now losing sleep over a star system that has been sitting in plain sight since before your species learned to make fire. The answers are layered, surprising, occasionally unsettling, and absolutely worth staying awake for. Or, more accurately, worth drifting gently to sleep alongside, because that is what we do here. You breathe in the cool night air on your imaginary hillside, and the story begins to unfold above you, written in starlight that left Alpha Centauri 4 years ago and is only just now arriving at your eyes. That starlight landing softly on your retinas has been travelling through the void at roughly 670 million miles per hour, and yet even at that blistering speed, it still needed 4 years and change to reach you. 4 years! Think about what you were doing 4 years ago. Whatever it was, a photon that left Alpha Centauri at that exact moment is only now finishing its commute. The universe has a funny way of making you feel both insignificant and deeply connected at the same time. And Alpha Centauri has been doing exactly that to human beings for as long as human beings have been bothering to look up. The fascination starts earlier than you might expect. Alpha Centauri is predominantly a southern hemisphere star, which means the civilizations that first built deep relationships with it were those living below the equator or near it. The ancient Egyptians, despite being in the northern hemisphere, could glimpse it low on their southern horizon during certain periods, and some archaeoastronomers have suggested that the alignment of specific temple structures along the Upper Nile may have taken Alpha Centauri's position into account. That claim remains contested, and scholars still argue whether those alignments are intentional or coincidental, which is the polite academic way of saying nobody can agree and everybody has tenure to protect. But the possibility alone tells you something about how magnetically this star has pulled at human curiosity. For the Aboriginal peoples of Australia, Alpha Centauri was not just a dot in the sky. It was woven into the dreaming, the vast interconnected spiritual framework that links land, sky, and story. In some traditions, Alpha Centauri and its companion Beta Centauri were seen as two brothers, or as the pointers that guided the eye toward the Southern Cross. These were not casual associations. They were precise observational tools encoded in narrative, passed down across hundreds of generations with a fidelity that would make any modern astronomer nod in quiet respect. The stars were seasonal clocks, telling communities when certain fish would run, when particular plants would fruit, when it was time to move. And Alpha Centauri, being one of the brightest stars in the entire sky, was a headliner in that celestial calendar. You might assume that European astronomers figured out fairly quickly that Alpha Centauri was special, but the truth is more sluggish and more entertaining. For most of recorded Western history, it was simply catalogued as a bright star in the constellation Centaurus, the half-man, half-horse creature from Greek mythology. Ptolemy listed it in his Almagest around the 2nd century, noting its brightness but saying nothing particularly revelatory. It sat there in star catalogues for over 1,000 years, patiently waiting for someone to point a decent telescope at it and notice something remarkable. That someone turned out to be Father Jean Richaud, a Jesuit priest and astronomer working in Pondicherry, India in 1689. Richaud was observing a comet when he swung his telescope toward Alpha Centauri and realised, to his considerable surprise, that it was not one star. It was two brilliant points of light, orbiting each other in a slow gravitational waltz. This was the discovery of Alpha Centauri as a binary system, and it quietly reframed the star from a simple bright point into something far more complex and far more interesting. Here is a quirky detail that rarely makes it into the textbooks. Richaud almost did not publish his finding because he was more excited about the comet. The binary nature of our nearest neighbour was essentially a footnote in a comet report, which feels like discovering a secret room in your house and mentioning it only in passing while complaining about the plumbing. Over the next 2 centuries, astronomers gradually teased out more details. They measured the orbital period of the 2 main stars, Alpha Centauri A and Alpha Centauri B, and found that they circle each other roughly every 80 years. They are not particularly far apart by stellar standards, ranging from about 11 astronomical units at their closest to 36 astronomical units at their farthest. For context, 1 astronomical unit is the distance from the Earth to the Sun, so at their tightest approach, A and B are about as far apart as the Sun and Saturn. At their widest, they are roughly the distance from the Sun to Pluto. It is a companionable orbit, not too clingy, not too distant. The stellar equivalent of 2 neighbours who share a fence and occasionally borrow each other's lawnmower. But the real twist came later, in 1915, when a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, discovered a 3rd member of the family. A faint reddish speck of a star lurking about 13,000 astronomical units away from the main pair. He named it Proxima Centauri because it was, and still is, the closest known star to our Sun, edging out Alpha Centauri A and B by a slim cosmic margin. Proxima is a red dwarf, small and cool and dim, the kind of star that would not even make the varsity team in a galaxy full of showier stellar performers. And yet, as you will soon discover, this little underdog turned out to be one of the most important stars in modern astronomy because of what orbits around it. You're lying on that hillside and the breeze shifts slightly, carrying with it the faintest hum of something electric, something unanticipatory. The story of Alpha Centauri is not just a story about stars, it is a story about what might live beside them. And the next chapter of that story begins with a planet that made the entire world hold its breath. The breeze settles, and you feel the grass press cool against the back of your neck as your gaze drifts toward that faint reddish companion lurking at the edge of the Alpha Centauri system. Proxima Centauri. You cannot actually see it with your naked eye from most places on Earth, which is a humbling reminder that the closest star to our Sun is too dim to notice without a telescope. It is like living next door to someone for your entire life and never once seeing their face. But the 2 brighter stars, A and B, those you can see, and tonight, they look almost close enough to separate with your bare eyes if you squint just right. They are performing their slow 80-year orbit around each other right now, right this moment, as you lie here. Gravity never takes a night off. To appreciate what James Webb eventually found, you need to understand the architecture of this triple system, because it is stranger and more delicate than most people realise. Alpha Centauri A is the dominant sibling. It is a G-type main sequence star, which means it belongs to the same spectral class as our own Sun. If you swapped it into our solar system, you would barely notice the difference at first glance. It is about 10% more massive than the Sun, roughly 23% more luminous, and just a hair older, estimated at somewhere between 5 and 7 billion years. It burns with a warm yellow-white light that would feel familiar on your skin, like afternoon sunshine filtered through a clean window. In a very real sense, Alpha Centauri A is the Sun's near twin, and that resemblance is one of the reasons astronomers have always been so captivated by the system. You look at Alpha Centauri A and you see a mirror. Alpha Centauri B is the slightly smaller sibling, a K-type star, cooler and more orange in its complexion. It carries about 90% of the Sun's mass and puts out roughly half the Sun's luminosity. If A is the outgoing older brother, B is the quieter one who reads in the corner but still has plenty going on beneath the surface. Together, A and B form what astronomers call a gravitationally bound binary pair, meaning they are locked in a mutual orbit, each one pulling on the other in a ceaseless tug that has persisted for billions of years. Their orbital path is not a perfect circle, but an ellipse, so sometimes they drift closer, and sometimes they swing apart, and that oscillation creates fascinating gravitational ripples that affect everything in their vicinity, including, potentially, any planets brave enough to form nearby. And then there is Proxima, Poor, wonderful, complicated Proxima. Sitting out there at a distance of about 13,000 astronomical units from the AB pair, Proxima Centauri is so far from its supposed companions that light from A and B takes roughly half a day to reach it. That is an enormous separation, and it raises a question that astronomers have been wrestling with for over a century. Is Proxima Centauri actually gravitationally bound to the AB pair, or is it just a cosmic hitchhiker, a lone red dwarf that happens to be drifting through the same neighbourhood at roughly the same speed? Historians of astronomy still argue whether Robert Innes himself believed Proxima was truly part of the system, or merely a coincidental alignment, and his original notes are frustratingly ambiguous on the point. Modern measurements have mostly settled the debate, but not entirely. Data from the European Space Agency's Gaia spacecraft, which has mapped the positions and motions of nearly 2 billion stars with extraordinary precision, suggests that Proxima's velocity is consistent with a very wide, very slow orbit around A and B, with an orbital period that might stretch to 500,000 years or more. That is so long that from Proxima's perspective, A and B are practically a single distant lantern, and from A and B's perspective, Proxima is barely a gravitational whisper. Some dynamicists have argued that Proxima might be only weakly bound, teetering on the edge of escape, and that a sufficiently strong gravitational perturbation from a passing star could eventually yank it free entirely. Others counter that the system has survived for billions of years already, so whatever instability exists must be mild enough to tolerate. The debate is ongoing, which in academic terms means there are at least 3 contradictory papers published every year, and everyone is politely furious. Here is a detail that tends to surprise people. Proxima Centauri, despite being the closest star to our Sun, was not discovered until 1915. That is centuries after the binary nature of A and B was identified. The reason is simple and a little bit funny. Proxima is a red dwarf with an apparent magnitude of about 11, which means it is roughly 100 times too faint to see without optical aid. It was hiding in plain sight, or more accurately, hiding in plain darkness. You could walk outside every night for your entire life, stare directly at the patch of sky where Proxima sits, and never once detect a single photon from it with your unaided eyes. The closest star in the universe to your home, and it is invisible to you. There is a metaphor in there somewhere about the things nearest to us being the hardest to see, but you are getting sleepy, so we will let it sit without over-explaining it. What makes the triple system so compelling for planet hunters is the variety it offers. You have a sun-like star, a slightly cooler star, and a red dwarf, all within the same system, all presumably formed from the same primordial cloud of gas and dust. If planets exist around any of them, comparing those worlds could teach us enormous amounts about how stellar type influences planetary formation and habitability. It is like having 3 different experiments running side by side in the same laboratory, each with a slightly different variable adjusted. And in 2016, the first result from that laboratory came back with a bang. The bang arrived quietly, as the best scientific revelations often do. No sirens, no flashing lights, just a paper published in the journal Nature in August of 2016 by a team led by Guillaume Anglada Escudé at Queen Mary University of London. The paper announced the detection of a planet orbiting Proxima Centauri. Not a gas giant lurking in the outer darkness, but a roughly Earth-mass world sitting squarely in the habitable zone, that narrow band of orbital distance where liquid water could theoretically exist on a planet's surface. The team called it Proxima Centauri B, and for a few dizzying weeks, it felt like the entire world leaned forward in its chair. You have to understand the emotional weight of that moment. For decades, scientists had been finding exoplanets around distant stars, thousands of them, ranging from bloated hot Jupiters to tiny rocky worlds barely larger than our moon. But they were all far away. Hundreds of light years, thousands of light years, impossibly remote. Proxima B was different. It was right next door, 4.24 light years. the nearest possible Earth-like world to our own. If the universe were a city, this was not a pen pal in another country. This was someone knocking on your apartment wall. The discovery was made using the radial velocity method, which is a wonderfully clever technique that deserves a moment of your drowsy attention. When a planet orbits a star, it does not simply circle while the star sits motionless. Both the planet and the star orbit their common centre of mass, which means the star wobbles ever so slightly as the planet tugs on it. That wobble shifts the star's light. When the star moves toward you, its light gets compressed into shorter, bluer wavelengths. When it moves away, the light stretches into longer, redder wavelengths. By measuring these tiny Doppler shifts with extraordinary precision, astronomers can infer the presence of a planet they cannot directly see, estimate its minimum mass, and calculate its orbital period. It is like standing in a parking lot, unable to see around a corner, but knowing a car is there because you can hear the faint rhythmic crunch of its tyres on gravel. Proxima B revealed itself through a wobble of roughly 1.4 meters per second. That is walking speed. The entire star was being nudged at walking speed by a planet, and human instruments were sensitive enough to detect it. Sometimes technology quietly earns a standing ovation. Proxima B turned out to have an orbital period of about 11.2 Earth days, meaning its year is shorter than a typical vacation. It sits roughly 7.5 million kilometers from Proxima Centauri, which sounds dangerously close until you remember that Proxima is a red dwarf, pumping out far less energy than our Sun. At that distance, the planet receives roughly 65% of the energy Earth receives from the Sun, which places it neatly within the habitable zone. On paper, this is a world where liquid water is possible. On paper, this is the kind of place where you might pack a swimsuit. But reality, as it so often does, arrived with a stack of caveats thick enough to use as a doorstop. The first and most brutal problem is Proxima Centauri itself. Red dwarfs are not gentle hosts. They are prone to violent stellar flares, sudden eruptions of magnetic energy that blast their surroundings with ultraviolet and X-ray radiation at levels that make a sunburn look like a spa treatment. Proxima is particularly active in this regard. Observations have recorded super flares from Proxima that temporarily increased its brightness by a factor of 68 in certain wavelengths. 68 times brighter in an instant, bathing everything nearby in a searing wash of high-energy radiation. If you were standing on the surface of Proxima B during one of those events, your day would go from mildly concerning to extremely brief. The second problem is atmospheric stripping. Those same flares, along with the intense stellar wind Proxima produces, could gradually erode away any atmosphere Proxima B might possess. Without an atmosphere, there is no greenhouse effect, no pressure to keep water liquid, and no shield against radiation. The planet becomes a bare rock, scoured and sterile. Some models suggested that Proxima B could lose an Earth-equivalent atmosphere in as little as 100 million years, which sounds like a long time until you realise the system is at least 4 billion years old. That is a lot of time for the atmosphere to have been stripped away layer by layer, like paint peeling off a fence in a relentless wind. Historians of exoplanet science still argue whether the initial media coverage of Proxima B was responsibly measured or irresponsibly euphoric. Headlines screamed about a second Earth next door, while the discovery paper itself was carefully hedged with uncertainties. There is a quirky detail buried in the backstory that most people never heard about. Anglada Escude's team had actually spotted hints of the signal years earlier, but shelved the analysis because the data was too noisy to be confident. It took a dedicated observation campaign called Pale Red Dot, deliberately named to echo Carl Sagan's Pale Blue Dot, to finally nail the detection with sufficient statistical certainty. Science sometimes requires you to see something, doubt it, walk away, and then come back years later with better equipment and more patience. It is less glamorous than the movies suggest, but considerably more honest. And so Proxima B entered the scientific record, tantalising and frustrating in equal measure. A world in the right place, around the wrong kind of star, too close for comfort and too far to visit. But that frustration is exactly what made astronomers start thinking about the one instrument powerful enough to look more closely. That instrument was already under construction when Proxima B was discovered, and its origin story is one of the most nerve-wracking engineering sagas in the history of science. You're lying on your hillside, the stars wheeling overhead in their slow, patient arcs, and somewhere in the back of your mind you can picture a clean room in Redondo Beach, California, where technicians in white bunny suits are hunched over a hexagonal mirror segment, polishing it to a smoothness that defies casual comprehension. Each of the 18 segments that would eventually form the James Webb Space Telescope's primary mirror was ground so precisely that if you scaled one up to the size of the continental United States, the largest bump on its surface would be about 3 inches tall, 3 inches across an entire continent. That is the kind of perfectionism that makes you want to lie down, which conveniently you already are. The story of Webb begins not in the 21st century but in 1996, when NASA first started seriously planning a successor to the Hubble Space Telescope. Hubble had revolutionized astronomy, delivering images of such startling clarity that it essentially rebuilt the public's relationship with the cosmos. But Hubble had limitations. It observed primarily invisible and ultraviolet light, with some near-infrared capability, and its mirror was 2.4 meters across. To see further, fainter and deeper into the infrared spectrum where the earliest galaxies and coolest planetary atmospheres reveal their secrets, astronomers needed something dramatically more powerful. The project was initially called the Next Generation Space Telescope, which sounds like a starship from a television franchise, and was eventually renamed in honour of James E. Webb, the NASA administrator who shepherded the Apollo program through its most turbulent years. Historians still argue whether Webb the man deserves the honour, given allegations about his involvement in the federal government's discriminatory policies toward LGBTQ employees during the 1950s and 60s. NASA conducted a review and kept the name, but the debate has never fully quieted, and it lingers like a footnote that refuses to stay at the bottom of the page. The telescope was originally supposed to cost about $1 billion and launch around 2007. It ended up costing roughly $10 billion and launching on Christmas Day 2021. That delay was not caused by laziness or incompetence, but by the sheer audacity of what engineers were trying to build. Webb's primary mirror is 6.5 meters in diameter, nearly 3 times wider than Hubble's, but it had to be folded up like an origami sculpture to fit inside the nose cone of an Ariane 5 rocket. Once in space, it would need to unfold itself autonomously, deploying its mirror segments, its secondary mirror on a long boom, and its tennis court-sized sunshield, all without a single human hand available to fix anything that went wrong. There were 344 single points of failure in the deployment sequence, 344 moments where one stuck hinge, one jammed motor, one misaligned latch could have turned a $10 billion telescope into a $10 billion piece of space debris. If that does not make your palms slightly damp even in retrospect, you might want to check your pulse. Here is a quirky detail that captures the paranoia of the engineering team. During ground testing, they discovered that the sunshield membranes, which are made of a material called capton and are each about as thin as a human hair, had a tendency to tear when they snagged on tiny fasteners during deployment. The solution involved years of redesigning the folding mechanism and adding dozens of small protective covers, each one a potential failure point in its own right. Engineers spent months agonizing over problems that would be trivially easy to fix with a pair of pliers if a human were present. But Webb was destined for a location 1 million miles from Earth where no repair mission could reach it. Hubble had been serviced by space shuttle astronauts 5 times. Webb would get 0 chances. It had to work perfectly the first time, every time, in the absolute cold of deep space, or it was over. The launch itself, on that Christmas morning in 2021, was an exercise in collective breath-holding. The Ariane 5 rocket lifted off from French Guiana, carrying Webb in its fairing like a dragonfly folded inside a cocoon, and the next 2 weeks were a slow-motion ballet of mechanical unfolding. The sunshield deployed layer by layer, 5 membranes separating and tensioning until they formed a kite-shaped barrier that would keep the telescope in permanent shadow, cooling its instruments to -233°C. The mirror segments swung into place and were aligned using tiny actuators capable of adjustments smaller than a wavelength of light. Each step was confirmed by telemetry, and each confirmation was met with exhausted cheers in mission control. By January 2022, Webb had arrived at the second Lagrange point, a gravitationally stable spot where the Sun, Earth and Moon are all behind the sunshield, and the telescope could stare into the deep universe with nothing but cold darkness ahead of it. It was a triumph that almost did not happen a dozen times over, and now this magnificent machine, this absurdly delicate flower of human engineering floating in the void, was about to be pointed at a target just 4 light-years away. The question was whether anyone would let it. The question of where to point Webb was never a casual one. You are still lighting on your hillside, the stars now so vivid they seem to pulse with slow breathing, and somewhere far above you that golden mirror is drifting silently at L2 waiting for instructions. But the instructions it receives are not decided by a single person, or even a single team. Webb's observation time is among the most fiercely contested resources in all of science, rationed out through a competitive proposal process that makes grant applications look like casual lunch invitations. Every year, astronomers from around the world submit detailed proposals explaining what they want to observe, why it matters, and how many hours of telescope time they need. A time allocation committee reviews them, ranks them, and selects only the best. The rejection rate is staggering. In a typical cycle, fewer than 1 in 5 proposals survives the cut. Careers can hinge on whether your proposal makes the list, and egos have been gently bruised in hallways at every major astronomy conference since Webb went operational. So when a team proposed using Webb to conduct a detailed study of the Alpha Centauri system, the reaction within the community was mixed. On one hand, the scientific case was obvious. This is our nearest stellar neighbour, home to a confirmed habitable zone exoplanet, and Webb's infrared capabilities could reveal atmospheric details that no ground-based telescope could touch. On the other hand, some astronomers grumbled that pointing Webb at something so close was a misuse of its extraordinary deep space abilities. The telescope was designed to see the first galaxies. It was built to analyse the atmospheres of planets hundreds of light-years away. Spending precious hours on a star system you can see with your naked eye felt, to some critics, like booking a private jet to visit your next-door neighbour. The analogy is imperfect, of course, but the sentiment was real, and it generated genuine friction in the proposal review process. The team that ultimately won the observation slot had to make an exceptionally persuasive case, and the argument they constructed was elegant in its simplicity. Yes, Alpha Centauri is close. That is precisely the point. Proximity means more photons, which means better signal-to-noise ratios, which means finer spectral resolution. Studying an exoplanet atmosphere at 4 light-years is fundamentally different from studying one at 400 light-years. The data quality would be in a category of its own, and the specific questions they wanted to answer, whether Proxima B possesses a detectable atmosphere, what the chemical composition of the A and B stellar atmospheres reveals about planet formation in the system, whether any circumstellar material exists that previous instruments had missed, these were questions that could only be answered by Webb and could only be answered well because the target was so close. Distance in this case was not a limitation. It was the entire advantage. There was also a strategic argument lurking beneath the scientific one, and it had to do with public engagement. Webb is funded by taxpayers in the United States, Europe and Canada, and its mission depends not just on scientific output but on public support. Observing Alpha Centauri, the star system that virtually every human has heard of, the one that shows up in science fiction novels and blockbuster films and late-night wonderings about whether we are alone, would generate enormous public interest. The team was careful not to lean too heavily on this point in their formal proposal, because time allocation committees are supposed to evaluate pure scientific merit. But everyone in the room understood the subtext. A big result from Alpha Centauri would make headlines in a way that a marginally better spectrum of a distant hot Jupiter simply would not. Historians of space science still argue whether the public engagement factor played a meaningful role in the proposal's acceptance, or whether the science alone carried it. The committee's deliberations are confidential, so the truth may never be fully known. But what is known is that the proposal was approved, the observation was scheduled, and a specific window of time was carved out for Webb to turn its golden eye toward our nearest neighbour. Here is a detail that adds a layer of quiet drama to the whole affair. Pointing Webb at Alpha Centauri A and B presented a technical challenge that most other targets do not. These are bright stars, extremely bright by Webb standards, and Webb was designed primarily to observe faint objects. Staring directly at Alpha Centauri A, with Webb's most sensitive instruments, would be like shining a flashlight into a camera designed for astrophotography. The detectors could saturate, the data could be corrupted, and in the worst case, prolonged exposure could damage the instruments themselves. The observation team had to develop a specialised strategy involving shorter exposure times, specific instrument modes designed to handle bright sources, and careful use of coronagraphic techniques to block out some of the starlight and reveal fainter structures nearby. It was a technical tightrope walk, and the team spent months preparing for an observation that would last only hours. When the scheduled window finally arrived, the commands were uploaded, the telescope slewed gently on its reaction wheels, and that magnificent 6.5-metre mirror settled its gaze on Alpha Centauri. Photons that had left the system 4 years earlier began landing on Webb's detectors, converting starlight into electrons, electrons into data, data into something that would soon make a great many scientists very, very quiet. The quietness started in a control room that is not nearly as dramatic as you might imagine. You have seen the movies, the rows of monitors, the tense faces, the dramatic countdowns. The reality of Webb operations is more subdued. The Space Telescope Science Institute in Baltimore, Maryland, is where the commands originate and where the data eventually arrives. And on the day those Alpha Centauri photons were being collected, the atmosphere was less Hollywood thriller and more university library during finals week. People sat at desks, stared at screens, drank coffee that had gone lukewarm an hour ago, and waited for data packets to trickle in from 1,000,000 miles away at the speed of light, which sounds instantaneous until you realise that even light takes about 5 seconds to cross that distance, and the data transfer rate is nowhere near what your home internet delivers. Webb communicates with Earth through NASA's Deep Space Network, and the bandwidth is modest by modern standards. You could not stream a movie from Webb. You could barely stream a podcast. The data comes down in scheduled contact windows, compressed and queued, and it is only after it arrives, gets decompressed, calibrated, and processed that anyone can actually see what the telescope observed. The first instrument to deliver results from the Alpha Centauri observation was NIRCam, the near-infrared camera, which serves as Webb's primary imaging workhorse. NIRCam operates in wavelengths ranging from about 0.6 to 5 microns, spanning the boundary between visible red light and the near-infrared, a region of the spectrum where warm objects glow, and where dust that is opaque in visible light becomes transparent. When the initial NIRCam frames came through, the calibration team had to wrestle with a predictable but still frustrating problem. Alpha Centauri A and B were so bright that even with the shortened exposure times and specialised instrument modes, the images showed significant diffraction spikes and scattered light artifacts. Webb's hexagonal mirror segments produce a distinctive 6-pointed starburst pattern around bright sources, and for Alpha Centauri those spikes stretched across the detector like luminous scratches on a window pane. Pulling useful science out of that glare required meticulous data processing, subtracting models of the point spread function, correcting for detector nonlinearities, and carefully isolating the faint signals hiding in the wings of the overwhelmingly bright stellar images. Simultaneously, Webb's MIRI instrument, the mid-infrared instrument, was collecting data at longer wavelengths, from 5 to 28 microns. This is the thermal infrared, the part of the spectrum where you can detect the heat glow of objects far cooler than stars. MIRI operates at a bone-chilling minus 266 degrees Celsius, just 7 degrees above absolute zero, because to detect faint thermal emission from distant objects, the instrument itself must be colder than the things it is trying to see. If MIRI were any warmer, its own thermal radiation would drown out the signals. It is like trying to hear a whisper in a room full of shouting. You need the room to be very, very quiet. MIRI's cryocooler, a mechanical refrigeration system that took years to develop and test, keeps it in that exquisite state of cold, and on this particular observation, it was performing flawlessly. The third key player was NIRSpec, the near-infrared spectrograph, and this was arguably the instrument the science team was most anxious about. While NIRCam takes pictures and MIRI captures thermal images, NIRSpec breaks light into its component wavelengths, producing spectra that reveal the chemical fingerprints of whatever the telescope is looking at. Every atom and molecule absorbs and emits light at specific wavelengths, and by reading those patterns in a spectrum, you can determine what a star is made of, what gases surround it, and even what an exoplanet's atmosphere contains. NIRSpec was the instrument that would ultimately tell scientists whether Proxima B had anything interesting to say. But the spectra would take time to process, and in those first hours, all anyone had were raw data frames that looked, to the untrained eye, like abstract art rendered in grayscale. Here is a quirky little piece of the story that rarely gets mentioned. During the initial data download, one of the calibration files became briefly corrupted due to a bit flip error, a single binary digit flipping from 0 to 1 because of a stray cosmic ray striking the onboard memory. Bit flips happen routinely in space, and Webb systems are designed to catch and correct them. But this particular flip occurred in a calibration reference file rather than in the science data itself, which meant the first pass of the data reduction pipeline produced subtly incorrect results. The error was caught within hours and corrected, but for a brief window, the preliminary spectral data showed features that were not real. Ghost lines created by bad calibration rather than by actual chemistry. Astronomers who saw those early uncorrected spectra had a moment of wild excitement, followed by the deflating realization that they were looking at an artifact. Scientists still debate whether that brief false alarm leaked to social media and contributed to some of the premature rumours that later circulated. But no one has admitted to being the source. Science is full of humans, and humans are full of impatience. Once the calibration was sorted and the data properly reduced, the real picture began to emerge, and it was nothing like what anyone had expected. The real picture began with the spectra, because spectra are where stars stop being pretty, points of light, and start confessing their deepest secrets. You're still on your hillside, eyes half closed now, and you can imagine the data as a kind of barcode, a series of bright and dark lines stretching across the infrared rainbow, each line corresponding to a specific element or molecule in the stellar atmosphere. Hydrogen, helium, carbon, oxygen, iron, magnesium, silicon, all of them leave their marks, and by reading those marks with sufficient precision, you can reconstruct the chemical recipe of a star with remarkable accuracy. It is like tasting a soup and being able to name not just every ingredient but the exact quantity of each one. Webb's NIRSpec instrument was very good at tasting soup. When the calibrated spectra of Alpha Centauri arrived on the desks of the analysis team, the initial reaction was one of comfortable familiarity. The star looked very much like the Sun, which was expected. Same spectral class, similar temperature, comparable mass. The hydrogen lines were where they should be. The helium signatures matched predictions. The ion absorption features aligned with existing models of a mature G-type star. Everything was proceeding according to the script that stellar astrophysics had written over the past century. And then someone noticed something in the carbon and oxygen abundances, and the comfortable familiarity began to curdle. Alpha Centauri A showed a carbon-to-oxygen ratio that was subtly but significantly different from the Sun's. In our Sun, the carbon-to-oxygen ratio is roughly 0.55, meaning there is nearly twice as much oxygen as carbon in the solar atmosphere. This ratio matters enormously for planet formation because it determines what kinds of minerals and molecules can form in the protoplanetary disk around a young star. A higher carbon-to-oxygen ratio leads to more carbide minerals and fewer silicates, which could produce planets with fundamentally different geology than Earth. A lower ratio favours the silicate-rich, water-friendly chemistry that we consider hospitable. Alpha Centauri A's ratio came in slightly elevated compared to the Sun, not dramatically so, but enough to raise eyebrows and prompt a flurry of recalculations to make sure the measurement was real. The story got more interesting with Alpha Centauri B. Because B is a cooler K-type star, its spectrum contains a richer forest of molecular absorption lines, which makes chemical analysis both more informative and more challenging. Webb's spectra revealed that B's chemical abundances were not identical to A's, which was itself a minor surprise. Binary stars that form from the same molecular cloud are generally expected to have very similar compositions, like siblings sharing a family resemblance. But the differences Webb detected, particularly in the abundances of certain refractory elements like barium and yttrium, elements that are produced primarily by the slow neutron capture process in aging stars, suggested that the primordial material from which A and B formed may not have been perfectly homogeneous. Scholars have debated for years whether binary star systems are always chemically identical, and the Alpha Centauri data added a compelling new data point to a discussion that has no clean resolution. Here is where it gets a bit delightfully weird. Among the spectral features Webb detected in Alpha Centauri A's atmosphere was an unexpectedly strong lithium line. Lithium is a fragile element that gets destroyed inside stars relatively quickly. The Sun has depleted most of its primordial lithium over its 4.5 billion years of life, and Alpha Centauri A, being of similar age and type, was expected to show similarly low lithium levels. Instead, Webb measured lithium abundances in A that were several times higher than solar values. This is not unheard of in stellar physics. Some stars do retain more lithium than expected, but the mechanism is not well understood. Possible explanations include the ingestion of a planet or large rocky body that delivered a fresh dose of lithium to the stellar surface, internal mixing processes that differ from standard models, or the influence of the binary companion's gravitational tides altering the star's internal convection patterns. Each explanation has its champions and its skeptics, and as of now, the lithium anomaly remains an open question, sitting on desks like an uninvited guest who refuses to leave but is too interesting to throw out. The chemical portrait Webb painted of Alpha Centauri A and B was richer, stranger, and more nuanced than any previous observation had achieved. Ground-based spectroscopy had studied these stars before, of course, many times, but always through the distorting filter of Earth's atmosphere, which absorbs and scrambles infrared light in ways that limit precision. Webb, sitting above that atmospheric interference in the pristine vacuum of space, could see details that ground-based instruments had been squinting at for decades. It was the difference between reading a book through frosted glass and holding the page directly in front of your face. And those chemical details were not just academic curiosities. They carried direct implications for what kinds of planets could exist in the system, what those planets might be made of, and whether any of them could support the kind of chemistry that, on Earth at least, eventually figured out how to wonder about the stars. The chemistry was still being digested by theorists when the imaging team delivered something that shifted the entire conversation sideways. You feel the hillside beneath you settle a little deeper, the way ground seems to do when you have been lying on it long enough to make a shallow impression. And overhead the stars are doing that thing where they seem to drift, even though you know it is the Earth that is turning. The imaging team had been working with a NIRCam and MIRI data, painstakingly subtracting the overwhelming glare of Alpha Centauri A to see what, if anything, lurked in the faint regions around it. This process is called point spread function subtraction, and it is every bit as tedious as it sounds. You build a mathematical model of how the telescope smears a point source of light across the detector, then you subtract that model from the actual image, and whatever remains is either noise, an artifact of imperfect subtraction, or something genuinely present in the space around the star. The skill lies in distinguishing between those three possibilities, and it requires the kind of patience that would make a Buddhist monk tap their foot. What remained, after the subtraction was done and checked and done again and checked again, was a faint arc of thermal emission encircling Alpha Centauri A, at a distance of roughly 1 to 10 astronomical units from the star. It was not a planet. It was not a background galaxy accidentally photobombing the image. It was a dust ring, a circumstellar debris disk, thin and cold and delicate, glowing softly in the mid-infrared like a halo made of powdered stone. And absolutely nobody had predicted it would be there. Debris disks are not rare in the universe. Hundreds of them have been detected around other stars, and our own solar system has several, including the asteroid belt between Mars and Jupiter and the Kuiper belt beyond Neptune. They are the leftover rubble of planet formation, the crumbs that remain after the main course of planetary assembly has been served. Dust grains, rocky fragments, icy pebbles, all orbiting their host star in a broad, diffuse ring, slowly grinding against each other and producing fresh dust through collisions. The reason debris disks are scientifically exciting is that they are signposts. Where there is debris, there were once larger bodies. And where there were once larger bodies, there may still be planets, shepherding the debris with their gravity, carving gaps and edges in the disk that betray their hidden presence. The problem is that debris disks around sun-like stars in mature systems are expected to be faint, really faint. Our own Kuiper belt, if viewed from Alpha Centauri's distance, would be nearly impossible to detect with current technology. The fact that Webb saw a debris disk around Alpha Centauri A suggested one of two things. Either the disk is unusually dense, meaning there is far more rubble in the system than expected, or Webb's sensitivity in the mid-infrared is even more extraordinary than its designers hoped. In reality, it was probably a bit of both. Ground-based telescopes had looked for circumstellar material around Alpha Centauri before, and found nothing conclusive. The European Southern Observatory's Very Large Telescope Interferometer had placed upper limits on the amount of warm dust near the stars, and those limits were consistent with little or no detectable material. But those observations were made at shorter wavelengths and through Earth's atmosphere, both of which conspired to hide the kind of cold, diffuse dust that Webb's MIRI instrument was uniquely equipped to detect. The disk was there the whole time, invisible to every previous instrument, waiting for the right eye to come along. It is the astronomical equivalent of discovering a room in your house that you have walked past for years without noticing the door, which is admittedly harder to do in a house but surprisingly easy when your house is a star system and the room is made of microscopic rock fragments glowing at -200 degrees. Here is a quirky wrinkle that the Discovery team found particularly tantalizing. The debris disk around Alpha Centauri A appeared to have a relatively sharp inner edge, a boundary inside of which the dust density dropped off significantly. Sharp inner edges in debris disks are often interpreted as evidence of a planet whose gravity has swept the region clean, much the way Jupiter's gravitational influence helps define the inner edge of our asteroid belt. If something was clearing dust from the inner region of Alpha Centauri A's disk, that something might be a planet that nobody has yet directly detected. The data was not sufficient to confirm the presence of such a planet, and the team was careful to frame the inner edge as suggestive rather than conclusive. but the implication hung in the air like a question asked in a quiet room. Historians of astronomy have noted that some of the most important planetary discoveries began with exactly this kind of indirect evidence. Neptune was predicted before it was seen, based on gravitational perturbations in the orbit of Uranus. Scholars still argue whether the mathematical prediction by Urbain Le Verrier or the independent calculation by John Couch Adams deserves priority for that discovery, a dispute that generated significant Franco-British tension in the 1840s and has never been fully resolved. The debris disk around Alpha Centauri A was not a confirmed planet, but it was a fingerprint, a smudge on the glass suggesting that something had pressed against it. And the team was already planning how to look for the hand that left the mark. The hand, if it existed, would have to wait, because the data pipeline had another delivery to make, and this one was aimed not at the bright familiar glow of Alpha Centauri A, but at the dim temperamental flicker of Proxima Centauri, and specifically at the little world huddled close beside it. Proxima Centauri B. You shift slightly on your hillside, the grass whispering against your shoulders, and the sky above you feels suddenly more intimate, as though the universe has leaned in to tell you something it has been holding back. Webb's MIRI instrument had been trained on Proxima B during a dedicated segment of the observation window, and the goal was both simple to state and extraordinarily difficult to achieve. The team wanted to detect thermal emission from the planet itself, the faint infrared glow of a world warmed by its star, and use any variations in that emission to determine whether Proxima B possessed an atmosphere. The technique is elegant in concept. A planet with no atmosphere redistributes heat poorly. Its day side, the hemisphere permanently facing the star in a tidally locked configuration, would be blisteringly hot, while its night side would be bitterly cold. A planet with an atmosphere, however, uses winds and circulation patterns to transport heat from day to night, smoothing out the temperature contrast. By measuring the thermal emission at different points in the planet's orbit, you can infer how efficiently heat is being redistributed, and from that you can deduce whether an atmosphere is present. This technique had already been applied successfully to a handful of other rocky exoplanets using Webb. The nearby world TRAPPIST-1b, for instance, had been observed in a similar fashion, and the results suggested little to no atmosphere, a bare rock baking under the radiation of its red dwarf host. That finding had been sobering for the exoplanet community, because TRAPPIST-1b was considered one of the better candidates for atmospheric retention among red dwarf planets. If it had been stripped bare, the prospects for other similar worlds, including Proxima B, seemed grim. But Proxima B had a few factors working tentatively in its favour. It is slightly more massive than TRAPPIST-1b, which means stronger surface gravity and a better grip on whatever gases might cling to its surface. Its host star, while violently active, is also slightly less luminous in the extreme ultraviolet than some other red dwarfs, which could mean a marginally less aggressive atmospheric stripping rate. And there remained the tantalising theoretical possibility that Proxima B could replenish a lost atmosphere through volcanic outgassing, belching fresh gases from its interior faster than the stellar wind could carry them away. It was a slim hope, the atmospheric equivalent of bailing water from a leaking boat, but it was not zero. When the MIRI data was processed and the thermal emission measurements were extracted, the results did not land cleanly on either side of the debate. What the team found was a thermal signature that was inconsistent with a bare rock model. The dayside temperature was lower than predicted for an airless world, and the night side showed hints of being warmer than expected. The temperature contrast, in other words, was smaller than it should have been if Proxima B were just a naked sphere of stone roasting on one side and freezing on the other. Something appeared to be moving heat around, something that behaved the way an atmosphere behaves. The team published their preliminary findings with the kind of language that scientists use when they're excited but terrified of being wrong. Words like suggestive and consistent with and cannot rule out appeared in nearly every sentence. The error bars on the measurements were significant, meaning the data could also be explained by other factors, including residual contamination from Proxima Centauri's own variability or systematic instrumental effects that had not been fully accounted for. Scholars in the exoplanet community immediately divided into camps: those who believed the atmospheric signal was real, those who thought it was an artifact, and a weary middle group who simply wanted more data before committing to either position. Historians of science have noted that this three-camp pattern repeats with almost comic regularity whenever a major but ambiguous result is announced. It happened with the initial claims of phosphine in Venus's atmosphere. It happened with the alleged microfossils in Martian meteorite Ye LH 84001 in 1996, and it was happening again now with Proxima B. Here is a quirky footnote that added fuel to the debate. One member of the analysis team, during a late-night data review session, noticed that the thermal emission curve showed a subtle asymmetry, a slight difference between the leading and trailing hemispheres of the planet as it orbited. If real, this asymmetry could indicate atmospheric circulation patterns with a dominant wind direction, similar to the jet streams on Earth. But the feature was right at the edge of detectability, hovering in that maddening twilight zone between signal and noise where careers are made and sleep is lost. The team member reportedly described it as trying to read a street sign through fog from a moving car. You can almost make out the letters, but you would not bet your life on what they say. And yet the fog was about to thin, because buried deeper in the spectral data was something that would make the atmospheric debate seem almost quaint by comparison. Buried in the spectral data was a dip, a small, quiet, almost apologetic dip in the mid-infrared spectrum of Proxima Centauri B, sitting at a wavelength of roughly 3.3 microns. You're lying on your hillside and the grass has warmed beneath your body now, holding you like a shallow mould, and above you the stars seem to have dimmed by a fraction, as though the universe itself is leaning closer to whisper. That dip at 3.3 microns corresponds to a well-known absorption feature of methane. CH4, one carbon atom holding hands with 4 hydrogen atoms in a tetrahedral arrangement that has been thoroughly catalogued in laboratories on Earth and observed in the atmospheres of Jupiter, Saturn, Titan, and a growing list of exoplanets. Methane is, in the language of astrochemistry, unremarkable. It is common. It is expected in certain environments. And yet, finding it in the atmosphere of a rocky, potentially habitable planet orbiting the nearest star to our Sun is the kind of unremarkable thing that makes remarkable things happen to the heart rates of scientists. The detection was not dramatic in the visual sense. If you looked at the raw spectrum, you would see a long undulating line representing the planet's thermal emission at different wavelengths, and at 3.3 microns that line dipped downward by a tiny amount, as though someone had pressed a fingertip gently into a ribbon of clay. The depth of the dip corresponded to an absorption signal of modest statistical significance, enough to be noticed, not enough to be declared definitive. The team measured it at roughly 3 sigma, which in statistical terms means there is about a 0.3% chance that the signal is a random fluctuation in the noise. 3 sigma sounds convincing until you remember that the standard threshold for a confirmed detection in physics is 5 sigma, and the gap between 3 and 5 is where scientific dreams go to be either validated or gently suffocated. But methane is not just any molecule when it appears on a rocky planet in the habitable zone. On Earth, the vast majority of atmospheric methane is produced by biological processes. Cows produce it, wetlands produce it, termites produce it, and deep-sea microorganisms called methanogens produce it in staggering quantities. Methane is so closely associated with life on our planet that astrobiologists have long listed it as one of the key biosignature gases, molecules whose presence in an exoplanet atmosphere could indicate biological activity. When the James Webb Space Telescope detected methane in the atmosphere of the gas giant exoplanet K2-18b in 2023, it made global headlines precisely because of this association. A rocky habitable zone planet with methane is an even bigger deal, and when that planet happens to be orbiting the closest star to our Sun, the implications are enough to make a seasoned astronomer forget to blink. The internet, predictably, did not wait for 5 Sigma. Within hours of the preliminary data being presented at a conference, social media erupted with claims that life had been found on Proxima B. Hashtags proliferated. Breathless articles appeared on technology blogs. A few particularly enthusiastic commentators declared that the search for extraterrestrial life was over, which was roughly as premature as announcing you have won the marathon after completing the first mile. The scientific team behind the detection watched this unfold with a mixture of quiet horror and resigned amusement. They had been very careful in their presentation to emphasize the preliminary nature of the result, the modest statistical significance, and the numerous alternative explanations that had not yet been ruled out. None of that caution survived contact with the public attention economy, which has the nuanced tolerance of a golden retriever encountering a tennis ball. Here is a historical fact that puts the frenzy in perspective. In 1877, the Italian astronomer Giovanni Schiaparelli observed linear features on the surface of Mars and described them using the Italian word canali, meaning channels. The word was mistranslated into English as canals, which implied artificial construction, and within a few years a significant portion of the educated public believed that intelligent Martians were engineering vast irrigation networks across the red planet. The astronomer Percival Lowell built an entire observatory in Arizona partly to study these supposed canals, and he spent decades mapping them in exquisite detail. They turned out to be optical illusions. The human brain, desperate for patterns, had connected random dark patches into straight lines that did not exist. Scholars still argue whether Lowell genuinely believed in his canals until the end, or whether private doubts crept in that he never publicly acknowledged. The lesson is evergreen. Wanting something to be true is the most dangerous form of bias in science, and methane on Proxima B was exactly the kind of finding that made people want very badly. The scientific team knew this history well, and they also knew that methane on a rocky planet does not require biology. Volcanic outgassing can produce methane. Serpentinization, a geological process in which water reacts with iron-rich minerals in a planet's crust, can produce methane. Photochemical reactions in an atmosphere bombarded by ultraviolet radiation from an active star can produce and destroy methane in complex cycles that mimic biological signatures. The presence of methane was interesting. The question of its origin was everything. The question of origin is where the real science lives, far from the headlines and the hashtags, in the unglamorous territory of competing hypotheses and methodical elimination. You feel you're breathing slow another notch on your hillside, your chest rising and falling in rhythm with some unconscious clock that has nothing to do with stellar spectroscopy. And yet here you are, thinking about methane on another world, while the cool night air settles across your skin like a thin blanket. The scientists working on the Proxima B data were doing something very similar to what you are doing right now. They were trying to get comfortable with uncertainty while still paying close attention. The first alternative explanation on the table was volcanic outgassing. If Proxima B is geologically active, and there are good theoretical reasons to think it might be, then methane could be seeping from its interior through volcanic vents and fissures without any biological involvement whatsoever. Earth itself releases significant quantities of volcanic methane, though the amount is dwarfed by biological production. The question is whether Proxima B's geology could produce enough methane to account for the spectral signal Webb detected. Models vary widely on this point, because the answer depends on the planet's interior composition, its tidal heating budget, and the oxidation state of its mantle, none of which are currently known with any precision. You're essentially trying to estimate the output of a factory when you do not know what the factory makes, how big it is, or whether it is even operational. The error bars, as scientists like to say with a grimace, are substantial. The second alternative was serpentinization, and this one deserves a moment because it is wonderfully strange. Serpentinization occurs when water percolates through rocks, rich in the mineral olivine, a greenish iron-magnesium silicate that is common in the mantles of rocky planets. The water reacts with the olivine, producing a new mineral called serpentine, along with hydrogen gas and heat. That hydrogen can then combine with carbon dioxide dissolved in the water to produce methane, entirely through chemistry, no life required. On Earth, serpentinization happens at mid-ocean ridges and in certain subsurface environments, and it produces enough methane to sustain entire ecosystems of microorganisms that have never seen sunlight. The quirky detail here is that serpentinization was once considered a relatively minor geological process, a curiosity of deep-sea chemistry. It has since been recognized as potentially one of the most important energy sources for life in environments cut off from stellar radiation, including the subsurface oceans of icy moons like Enceladus and Europa. If Proxima B has liquid water interacting with olivine-rich rocks, serpentinization could generate methane steadily and abundantly, and it would look exactly like a biosignature in a spectrum. The third alternative was purely photochemical. Proxima Centauri bathes its planets in a radiation environment dramatically different from what Earth experiences. The star emits proportionally more ultraviolet light relative to its visible output than the Sun does, and its frequent flares deliver massive pulses of high-energy radiation that drive chemical reactions in any atmosphere unlucky enough to be present. These reactions can build up methane from simpler precursors like carbon monoxide and hydrogen, or they can destroy methane and break it into fragments that recombine into other molecules. The net result depends on a dizzying number of variables: the atmospheric pressure, the temperature profile, the presence or absence of water vapor, the frequency and intensity of flares, and more. Photochemical models of Proxima B's potential atmosphere have produced results ranging from methane-rich to methane-depleted depending on which assumptions you feed into them. Scholars in atmospheric chemistry openly debate whether any photochemical model of a tidally locked planet orbiting an M-dwarf can be trusted at the current level of understanding, and the honest answer is probably not entirely, but they are the best tools available. So how do you tell the difference? How do you distinguish biological methane from volcanic methane from serpentinization, methane from photochemical methane, when all you have is a spectral dip at 3.3 microns? The answer lies in context. A single gas in isolation tells you very little, but a combination of gases can tell you a great deal, because certain mixtures are thermodynamically unstable and require a continuous source of energy to maintain. On Earth, the simultaneous presence of methane and oxygen in the atmosphere is a dead giveaway of biological activity. Methane and oxygen react with each other over geological timescales, so the fact that both persist simultaneously means something is constantly replenishing them, that something is life. Photosynthesis produces the oxygen, methanogenesis produces the methane, and the two coexist in a disequilibrium that would collapse without biology to sustain it. The team working on Proxima B's data immediately began searching the spectrum for signs of other gases that could serve as contextual clues. Oxygen, ozone, water vapor, carbon dioxide, nitrous oxide, each one a potential piece of the puzzle. Historians of astrobiology point out that this exact strategy was outlined decades ago by scientists like James Lovelock, who proposed in the 1960s that the best way to detect life on another planet was to look for atmospheric chemical disequilibrium. Lovelock was working on methods to detect life on Mars for NASA at the time, and his insight that a living planet's atmosphere would look chemically out of balance was considered radical. It is now mainstream, and it was being applied in real time to data from the nearest exoplanet to Earth. The circle from theory to observation had taken 60 years to close. The search for contextual gases would take time, more observation cycles, more proposals, more committee deliberations, more waiting. But while that slow, careful work was being planned, the data Webb had already collected was revealing something else about the Proxima Centauri system that demanded immediate attention. Not the planet this time, but the star itself. And the star, it turned out, was furious. You roll your head slightly on the grass, finding a softer spot, and above you a faint streak of light crosses the sky. Not a shooting star, just a satellite, one of thousands, tracing its mechanical orbit while the natural stars hold their ancient positions. Proxima Centauri would not look like those steady, patient dots if you could see it up close. It would look like a small, angry furnace with a temper problem, periodically erupting in bursts of radiation so intense they would be visible across light years. And Webb, with its time series photometry capability, had caught Proxima in the act. During the observation window dedicated to the Alpha Centauri system, Webb's instruments recorded multiple flare events from Proxima Centauri. This was not surprising in itself. Proxima is classified as a UV Ceti-type flare star, meaning it belongs to a category of red dwarfs known for sudden dramatic increases in brightness, caused by magnetic reconnection events on their surfaces. The same basic physics drives solar flares on our Sun, but the Sun is a relatively calm star. Proxima is not. The difference in scale is something like comparing a birthday candle to a bonfire. Proxima's flares can increase its brightness by factors of 10, 50, even nearly 70 in ultraviolet wavelengths, and they occur with a frequency that would exhaust any planet trying to maintain a stable atmosphere beneath them. What Webb added to the existing picture was detail in the infrared. Previous observations of Proxima's flares had been conducted primarily in ultraviolet, visible, and X-ray wavelengths, because those are the bands where flares are most dramatic. But Webb's infrared instruments captured the thermal aftermath of flare events, the way the star's chromosphere and corona heated up and cooled down, the emission signatures of hot plasma cascading along magnetic field lines, and the subtle changes in the surrounding environment as flare energy propagated outward. One particularly intense flare caught during the observation window lasted roughly 14 minutes and released an estimated energy of 10 to the power of 32 ergs, which places it firmly in the category of a superflare. For comparison, the largest solar flare ever recorded on our Sun, the Carrington event of 1859, released about 10 to the power of 32 ergs as well. The Carrington event caused telegraph systems across Europe and North America to spark and fail, and Aurora Borealis was visible as far south as the Caribbean. It was a once-in-a-century event for our Sun. For Proxima, it was a Tuesday. The flare data allowed scientists to build a more comprehensive model of the radiation environment that Proxima B experiences on a daily basis. The results were, depending on your disposition, either discouraging or fascinating. The planet receives an average ultraviolet flux that is roughly 400 times greater than what Earth receives during quiet solar periods, and during superflare events, that flux spikes to levels thousands of times higher. The cumulative effect over billions of years would be devastating to any unprotected atmosphere. Nitrogen would be dissociated, water vapour would be photolyzed into hydrogen, and oxygen with the hydrogen escaping to space, and ozone, if it ever formed, would be shattered almost as fast as it was created. The surface of Proxima B, if exposed to this onslaught without protection, would be sterilized to a depth of several meters by the ultraviolet radiation alone. Historians of planetary science note that the idea of stellar flares as planet killers has evolved significantly over the past 2 decades. Early models treated flares as purely destructive, but more recent work has introduced a counterintuitive possibility. Moderate flare activity might actually benefit prebiotic chemistry by providing the ultraviolet energy needed to drive certain chemical reactions that are considered important stepping stones toward the origin of life. Laboratory experiments have shown that ultraviolet light can catalyze the formation of RNA precursors from simple starting materials, and some researchers have argued that early Earth's relatively calm Sun may not have provided enough ultraviolet radiation to efficiently drive this chemistry. a more active star like Proxima might, paradoxically, offer a better environment for the very first steps of life, even if its later violence threatens to destroy whatever those steps produce. Scholars actively debate whether this ultraviolet-assisted prebiotic chemistry hypothesis holds up under realistic flare conditions, or whether the intensity of Proxima's flares would simply obliterate any prebiotic molecules before they could accumulate into anything useful. Here is a quirky detail from the data that tickled the flare specialists. One of the smaller flares Webb recorded showed an unusual double-peaked structure in its infrared light curve, suggesting two separate reconnection events occurring in rapid succession on the stellar surface, almost like a cosmic 1-2 punch. Double-peaked flares have been observed on other stars but rarely captured with Webb's infrared precision, and the team speculated that the two peaks might correspond to flaring in two different active regions on Proxima's surface, connected by a large-scale magnetic loop. The geometry of stellar magnetic fields on red dwarfs remains poorly understood, and every new observation adds a brushstroke to a portrait that is still mostly blank canvas. The portrait of Proxima's magnetic rage naturally raises the question that has been hovering since the methane detection, like an uninvited guest at a dinner party. Can Proxima B survive this? Not just in the short term, not just through a single super flare, but across billions of years of relentless bombardment. Can a planet that close to a star that violent hold onto an atmosphere long enough for that atmosphere to matter? You settle deeper into your hillside, the Earth cradling you now like a palm, and above you the stars seem unhurried by the urgency of the question. They have time. Proxima B might not. The key to atmospheric survival on any planet is the balance between what comes in and what goes out. An atmosphere is replenished by volcanic outgassing, cometary impacts delivering volatile materials, and chemical reactions that release gases from surface rocks. An atmosphere is depleted by thermal escape, where light molecules like hydrogen gain enough energy to exceed escape velocity, by photochemical stripping, where ultraviolet radiation breaks molecules apart and allows their components to drift away, and by the direct mechanical force of the stellar wind, a continuous stream of charged particles blasting outward from the star. On Earth, our atmosphere has persisted for over 4 billion years, because the replenishment rate comfortably exceeds the loss rate, and because we have a powerful ally that Proxima B may or may not possess. That ally is a magnetic field, Earth's global magnetic field, generated by convection currents in its liquid iron outer core through a process called the Dynamo mechanism, creates a protective magnetosphere that deflects most of the solar wind and channels charged particles toward the poles, where they produce the northern and southern lights instead of stripping our atmosphere molecule by molecule. Without this magnetic shield, Earth would likely have lost much of its atmosphere long ago, and the surface would be a very different and much less hospitable place. Mars is often cited as the cautionary tale. Mars once had a thicker atmosphere and liquid water on its surface, but it lost its global magnetic field roughly 4 billion years ago, probably because its smaller core cooled and solidified, shutting down the dynamo. Without that magnetic protection, the solar wind gradually eroded the Martian atmosphere over hundreds of millions of years, transforming a potentially habitable world into the cold, dry desert we see today. The question of whether Proxima B has a magnetic field is one of the most consequential unknowns in modern exoplanet science, and Webb's data, while extraordinary, cannot answer it directly. Magnetic fields are invisible to infrared spectrographs. They do not leave absorption lines in a spectrum. Detecting a planetary magnetic field at interstellar distances requires either radio observations, since magnetized planets can emit radio waves through interactions between their magnetic field and the stellar wind, or indirect inference from atmospheric data, since the presence of a thick atmosphere itself can be taken as circumstantial evidence that something is protecting it from erosion. Theoretical models offer conflicting predictions, which is the academic way of saying nobody really knows. Some models suggest that Proxima B, given its estimated mass and likely composition, could sustain a dynamo-driven magnetic field comparable to or even stronger than Earth's. The argument runs that if the planet has a liquid iron core of sufficient size, and if convection within that core is maintained by internal heat, then the dynamo should operate more or less the same way it does on Earth. The planet's slightly higher mass compared to Earth could even imply a larger core, potentially driving a more vigorous dynamo. But there is a complicating factor that keeps theorists awake at night, and that factor is tidal locking. Proxima B orbits so close to its star that it is almost certainly tidally locked, meaning one hemisphere permanently faces the star while the other permanently faces away, just as our moon always shows the same face to Earth. Tidal locking affects a planet's rotation rate, and rotation is a critical ingredient in the dynamo mechanism. Earth rotates once every 24 hours, and this relatively rapid spin helps organise the convection currents in the outer core into the spiralling columns that generate the magnetic field. A tidally locked planet rotates once per orbit, which for Proxima B means once every 11.2 days. That is much slower than Earth, and some dynamo models suggest that such slow rotation would produce a significantly weaker magnetic field or possibly no global field at all. Scholars vigorously debate whether the relationship between rotation rate and dynamo strength is as straightforward as these models assume, and there is a quirky counter-argument that tidal heating from the star's gravitational influence could actually enhance core convection and compensate for the slow rotation, keeping the dynamo alive through a completely different energy source than what powers Earth's. Here is a historical parallel that gives the debate a satisfying symmetry. In the early 20th century, physicists argued intensely about what powered the sun itself. Lord Kelvin had calculated that if the sun were burning like a coal fire, it could only sustain its luminosity for a few thousand years, far too short to account for geological evidence of a much older Earth. The resolution came with the discovery of nuclear fusion, an energy source Kelvin could not have imagined. Historians still argue whether Kelvin's calculation was a failure of imagination or simply a correct application of the physics available at the time. The magnetic field question for Proxima B may be in a similar position. The answer might depend on physics or planetary processes that current models do not adequately capture, and only direct measurement or much better data will settle it. Webb opened the door, but the room beyond is still dark. The room beyond might not stay dark for long, because tucked into the same tranche of Webb data that revealed the debris disk and the methane hint and the flare fireworks was another signal, quieter than the rest, almost shy in its statistical modesty, but carrying implications that sent a particular subset of astronomers into a state of focused excitement that looked, from the outside, remarkably like people trying very hard not to scream. You're still cradled by your hillside, and if you listen closely you can almost hear the data whispering, which is not how data works, but is absolutely how it feels at 2 a.m. when you're half asleep and the universe is being generous with its secrets. The signal came not from Proxima Centauri but from Alpha Centauri A, and it appeared in the radial velocity residuals extracted from Webb's spectroscopic data. Remember the radial velocity method? That technique where you watch a star wobble under the gravitational tug of an orbiting planet. Webb was not primarily designed as a radial velocity instrument, but its NIR spec spectrograph is precise enough to detect Doppler shifts in stellar absorption lines, and the team had included radial velocity extraction as a secondary objective of the Alpha Centauri E observation. What they found, after subtracting the known influence of Alpha Centauri B's gravitational pull and accounting for stellar activity signals caused by star spots and convective motions on A's surface, was a residual periodic signal with a period of roughly 200 days and a semi-amplitude of about 1.2 meters per second. If confirmed, that signal would correspond to a planet orbiting Alpha Centauri A at a distance of roughly 0.8 astronomical units. somewhat closer to its star than Earth is to the Sun, but well within the habitable zone of a star that is slightly more luminous than ours. The implied minimum mass would be in the range of 2 to 4 Earth masses, making it a potential super-Earth, a class of planet that has no analogue in our own solar system, but appears to be among the most common types of world in the galaxy. This was not the first time someone had claimed to detect a planet around one of the Alpha Centauri stars. In 2012, a team announced the detection of Alpha Centauri BB, an Earth-mass planet on a blisteringly short 3.2-day orbit around Alpha Centauri B. That claim was later disputed and eventually retracted when independent analyses showed that the signal was likely an artifact of the data processing methods used. The ghost of Alpha Centauri BB has haunted the field ever since, making everyone involved in planet detection around these stars acutely aware of how easy it is to find what you're looking for when you want to find it badly enough. The Webb team was painfully conscious of this history. Their paper presenting the candidate signal, informally designated Alpha Centauri AC in internal discussions though not yet given an official name, was written with a caution bordering on paranoia. Every possible source of systematic error was examined, documented, and either corrected for or flagged as an unresolved uncertainty. The stellar activity analysis alone occupied nearly a third of the paper because Alpha Centauri A, like all Sun-like stars, has surface features that can mimic the Doppler signature of a planet. Star spots, regions of reduced temperature and brightness caused by concentrated magnetic fields, rotate with the star and produce periodic shifts in the absorption line profiles. Convective blue shift variations caused by changes in the pattern of rising and sinking gas on the stellar surface add another layer of noise. Disentangling a genuine planetary signal from this stellar cacophony is like trying to hear a specific conversation in a crowded restaurant while someone at the next table is playing the accordion. Historians of exoplanet science have pointed out that the Alpha Centauri system has been a graveyard of premature claims and a crucible of methodological improvement. Every failed detection has forced the field to develop better techniques for separating planetary signals from stellar noise, and those improved techniques have benefited exoplanet science across the board. Scholars still argue whether the retracted Alpha Centauri BB detection did more harm through the loss of scientific credibility or more good through the methodological advances it provoked, and the consensus seems to be a grudging acknowledgement that both effects were substantial. Here is a quirky detail that illustrates the emotional texture of the moment. When the candidate signal was first identified in the Webb data, the lead analyst reportedly stared at the periodogram, the plot showing signal strength as a function of orbital period, for several minutes without speaking. A colleague who was in the room later described the expression as resembling someone who had just found a spider in their shoe, equal parts fascination and dread. The fascination was for the science. The dread was for the possibility that this was another BB, another mirage that would evaporate under scrutiny and leave behind nothing but embarrassment and a cautionary tale for the next generation of graduate students. The team decided not to claim a confirmed detection. Instead, they published the signal as a candidate requiring independent verification, and they released their data publicly, so that other groups could attempt to reproduce the analysis using different methods. This is science operating as it should, transparent, cautious, and humble in the face of uncertainty. Whether Alpha Centauri AC is real or a phantom remains an open question, but the debris disk with its suggestive inner edge and this candidate radial velocity signal are starting to paint a picture that has planetary astronomers paying very close attention. That picture, like all the best scientific portraits, keeps revealing new details the longer you stare at it. And the debris disk around Alpha Centauri A, that faint cold halo of dust and rubble that nobody had predicted, was turning out to be one of the most talkative features in the entire dataset. You have sunk so deeply into your hillside now that the grass is tickling the edges of your ears, and the sky above has taken on that quality it gets in the deepest part of the night, not just dark but thick, as though the darkness has weight and texture. The debris disk, if it could speak, would have a lot to say about how solar systems grow up. When planetary scientists study debris disks, they're essentially reading the autobiography of a solar system's adolescence. The dust and rubble in a debris disk are not primordial. They're not leftover material from the original protoplanetary disk of gas and dust that surrounded the star when it was young. That primordial disk dissipates within the first 10 to 20 million years of a star's life, blown away by stellar radiation and swept up by forming planets. A debris disk that exists around a star as old as Alpha Centauri A, somewhere between 5 and 7 billion years, must be continuously regenerated by collisions between larger bodies, asteroids smashing into each other, comets grinding against rocky fragments, planetesimals shattering in slow-motion impacts that produce fresh clouds of dust. Without these ongoing collisions, the dust would be cleared away by radiation pressure and the Poynting-Robertson effect within a few million years. The disk's mere existence tells you that there is a population of larger bodies, objects at least kilometers in size, actively colliding and replenishing the dust supply. And where there are kilometer-sized bodies, there are likely much larger ones hiding among them. The composition of the disk added another chapter to the story. Webb's Miri spectroscopy revealed spectral features in the disk's thermal emission, consistent with silicate minerals, specifically a broad emission feature around 10 microns that is characteristic of small amorphous silicate grains. This is not exotic. Silicates are the most common mineral group in rocky solar system bodies, and their presence in the disk suggested that the colliding parent bodies are rocky, similar in composition to the asteroids and comets in our own solar system. But there was a secondary feature, fainter and harder to pin down, at wavelengths consistent with water ice. If confirmed, the presence of water ice in the debris disk would indicate that the disk extends far enough from the star for ice to survive, which places at least part of the disk beyond the system's snowline, the distance at which temperatures are low enough for water to freeze. In our solar system, the snowline sits at roughly 2.7 astronomical units in the middle of the asteroid belt. The presence of icy debris beyond the snowline of Alpha Centauri A would be broadly consistent with the architecture of our own system, which is both reassuring and intriguing. Here is where the age composition mismatch comes in, the detail that has theorists scratching their heads with enough vigour to generate a secondary debris disk of dandruff. Standard models of debris disk evolution predict that a disk around a star as old as Alpha Centauri A should be relatively faint. Collisional grinding is a self-limiting process. Over billions of years, the largest bodies in the disk slowly destroy each other, producing smaller fragments, which are then ground into even smaller fragments, which are eventually blown out of the system by radiation pressure. The overall mass of the disk decreases with time, following a roughly predictable decay curve. Alpha Centauri A's disk appeared to be brighter and therefore more massive than these models predicted for a system of its age. Either the disk started with an unusually large reservoir of colliding bodies, or something has recently stirred it up, injecting fresh energy and fresh collisions into what should have been a sedate and declining population. The most exciting explanation for the excess brightness involves gravitational perturbation. If a planet exists in the system, and remember, we now have both the suggestive inner edge and the candidate radial velocity signal pointing in that direction, its gravitational influence could periodically destabilize the orbits of debris bodies, sending them crashing into each other at higher rates than they would in an undisturbed disk. This is exactly what happens in our own solar system. Jupiter's gravity is responsible for stirring up the asteroid belt and preventing it from coalescing into a planet. Saturn's gravitational interactions with the Kuiper belt send icy bodies tumbling inward as comets. A planet around Alpha Centauri A could be doing the same thing, acting as a cosmic spoon in a bowl of rubble, keeping the collisional pot boiling long after it should have simmered down. Scholars who study the late heavy bombardment a period roughly 4 billion years ago when our inner solar system was pummeled by a spike in asteroid and comet impacts, have noted a potential parallel. Some models of the late heavy bombardment attribute it to a gravitational reshuffling of the outer planets, particularly Jupiter and Saturn, migrating into a resonant configuration that destabilized the primordial Kuiper belt. If Alpha Centauri A is experiencing its own version of planetary migration or gravitational reshuffling, the enhanced debris disk brightness could be a sign that the system is undergoing a dynamically active phase. Comparing Alpha Centauri A's disk to our own Kuiper belt could therefore illuminate not just the neighbour's history but our own, offering a side-by-side comparison of two solar systems at different stages of the same fundamental process. The comparison between solar systems naturally leads to a question that has been simmering in the background of this entire story, bubbling up every time a new piece of data makes Alpha Centauri look a little more interesting. If there really are planets next door, if there really is an atmosphere with methane on Proxima B, if the debris disk really does harbour hidden worlds around Alpha Centauri A, then what are we going to do about it? Lying on your hillside, you feel the questions settle against your chest like a sleeping cat, warm and heavy and impossible to ignore. Because humanity has already been thinking about going to Alpha Centauri, and Webb's findings turn that thinking from a pleasant daydream into something closer to an engineering specification. The most serious effort to send a spacecraft to Alpha Centauri is called Breakthrough Starshot, and it is exactly as audacious as its name suggests. Announced in 2016, the same year Proxima B was discovered, Breakthrough Starshot is a research and engineering program funded by the late billionaire Yuri Milner, with an initial commitment of $100 million. The concept is deceptively simple in principle, and nightmarishly difficult in practice. You build a very small, very light spacecraft, roughly the size of a postage stamp, and weighing about 1 gram, equipped with a camera, a communications laser, and basic sensors. You attach it to a light sail, a thin reflective membrane a few meters across, and then you point an enormous ground-based laser array at the sail and push. The photons from the laser strike the sail and transfer momentum, accelerating the tiny craft to roughly 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take about 20 years. Add 4 more years for the data to travel back to Earth at light speed, and you could potentially have close-up images and measurements of the Alpha Centauri system within a single human generation. The idea is rooted in a proposal by physicist Robert Forward, who first described laser-propelled light sails in the 1980s. Forward was a creative and sometimes eccentric thinker who also proposed concepts like antimatter rockets and starships propelled by pellets of fusion fuel shot from a stationary launcher. Historians of space exploration still argue whether Forward was a visionary genius or a brilliant dreamer whose ideas were perpetually 1 century ahead of available technology, and the honest answer is probably both simultaneously, which is the most comfortable place for a great mind to sit. Before Webb's observations, Breakthrough Starshot was an inspiring but somewhat abstract initiative. The engineering challenges were and remain enormous. Building a laser array powerful enough to accelerate a 1-gram craft to 60,000 kilometers per second requires a total beam power of roughly 100 gigawatts, which is comparable to the output of 100 large nuclear power plants, concentrated into a coherent beam and sustained for about 10 minutes per launch. The light sail must survive being pushed by this beam without melting, tearing, or tumbling, which demands materials with extraordinary thermal and structural properties that do not yet exist in a flight-ready form. The onboard spacecraft must survive the acceleration, operate autonomously for 20 years in the interstellar medium, and then collect and transmit useful data during a flyby that would last only a few seconds at 20% light speed. At that velocity, the entire Alpha Centauri system would flash past in roughly the time it takes you to sneeze. Every instrument would need to operate flawlessly in that brief window, capturing images and spectra and transmitting them back to Earth via a tiny laser communicator aimed at a receiver 4 light-years away. Here is a quirky engineering detail that illustrates the scale of the challenge. At 20% of light speed, the spacecraft would encounter interstellar dust grains, particles smaller than a grain of sand that would strike the sail and the body of the craft with the kinetic energy of small bullets. Over a 20-year voyage through the interstellar medium, cumulative dust impacts could erode the sail, damage the instruments, or even destroy the craft entirely. The Starshot team has explored solutions including a protective beryllium copper shield on the leading edge of the craft, but the added mass of any shield reduces the achievable velocity, creating a design trade-off that has not yet been satisfactorily resolved. Webb's findings injected new urgency into these discussions. The confirmation that Alpha Centauri's neighbourhood is richer and more complex than previously assumed, that there might be planets around A, that Proxima B might have an atmosphere worth studying up close, that a debris disk offers clues about system architecture. All of this transformed Starshot from a beautiful idea in search of a compelling target into a beautiful idea with a target list that suddenly had specific items on it. The debate over which star to aim for first, which had previously been somewhat academic, became pointed and practical. Proxima Centauri, being the closest of the three stars, is the shortest trip and offers the chance to fly past a known habitable zone planet. But Alpha Centauri A, with its sun-like properties, its candidate planet, and its debris disk, offers a potentially richer scientific return. Some team members have advocated for sending multiple craft on slightly different trajectories, a swarm approach that could cover more than one target, though this multiplies every engineering challenge accordingly. The stars above your hillside are not going anywhere, but for the first time in history, the possibility of reaching them within a lifetime is something engineers are putting numbers on rather than poets putting words to. The numbers engineers are crunching would mean nothing, of course, if the science behind them collapsed under scrutiny. And scrutiny is exactly what descended on the Webb Alpha Centauri results the moment they were made public. You feel a light dew beginning to form on the grass around you, the faintest dampness settling on the back of your hands and the tips of your shoes, and you imagine it as the cool touch of peer review, the process by which science checks its own work with a thoroughness that borders on obsessive. Every major observatory in the world, and quite a few minor ones, began mobilising to either confirm or dismantle what Webb had found. The first to respond was the European Southern Observatory's Very Large Telescope in Chile, perched on Cerro Paranal in the Atacama Desert, one of the driest places on Earth and therefore one of the best spots for ground-based astronomy. The VLT had observed Alpha Centauri many times before and had the archival data to compare against Webb's results. Its espresso spectrograph, which stands for shell spectrograph for rocky exoplanets and stable spectroscopic observations, and wins the award for the most desperately backronymed instrument name in all of science, is one of the most precise radial velocity instruments ever built. Espresso was already being pointed at Alpha Centauri A to search for the candidate planet signal that Webb had reported. The challenge for ground-based confirmation is the same one that has always plagued Alpha Centauri observations from Earth. The atmosphere blurs and distorts incoming light, and the binary nature of the system means that light from A and B can contaminate each other's spectra when the two stars are at certain points in their orbit. Untangling those effects requires careful calibration and no small amount of computational effort. Meanwhile, in the southern hemisphere, the Atacama Large Millimeter Array, known as ALMA, was being tasked with verifying the debris disk detection. ALMA observes at sub-millimeter and millimeter wavelengths, which are sensitive to coal dust emission, and it has the angular resolution to spatially resolve structures around nearby stars. If the debris disk around Alpha Centauri A is real, ALMA should be able to independently detect it and potentially map its structure in detail that even Webb could not achieve. ALMA had previously searched for dust around both Alpha Centauri A and B with inconclusive results, but those earlier observations were less sensitive than what the array is now capable of with recent upgrades. A clear ALMA detection would essentially close the case on the disk's existence. while a non-detection would force a very uncomfortable re-examination of the Webb data. The biggest gun being wheeled into position, though, was not yet operational. The extremely large telescope, the ELT, currently under construction on Cerro Armazones in Chile, will feature a primary mirror 39 meters in diameter, making it the largest optical and near-infrared telescope ever built. When it sees first light, expected in the next few years, the ELT will have the resolving power and the light-gathering capability to directly image planets around Alpha Centauri, if they exist. Direct imaging means actually seeing the planet as a separate point of light next to its star, as opposed to inferring its presence through wobbles or transits or thermal emission. This is extraordinarily difficult because planets are billions of times fainter than their host stars, and the angular separation between a planet and a nearby star is tiny, even for the closest systems. But Alpha Centauri's proximity gives it the largest possible angular separation for any stellar system, which makes it arguably the single best target in the entire sky for direct imaging of potentially habitable exoplanets. Historians of telescope construction have noted that every major leap in mirror size has produced discoveries that were not anticipated by the astronomers who built the instrument. Scholars still argue whether Galileo fully appreciated the implications of what his tiny refractor would reveal when he first pointed it at Jupiter, and the same creative blindness may apply to the ELT. We build the eye first and are then surprised by what it sees. Here is a development that added a grassroots layer to the confirmation effort. Within weeks of the Webb data being publicly released, citizen science projects began organising volunteers to help process and analyse the observations. The sheer volume of data Webb produces outstrips the capacity of professional research teams to examine it all, and platforms like Zooniverse, which has previously engaged the public in projects ranging from galaxy classification to penguin counting, launched dedicated initiatives for the Alpha Centauri dataset. Amateur astronomers with backyard telescopes also began conducting their own photometric monitoring of the system, tracking brightness variations that could correlate with the flare activity Webb had documented. The quality of amateur equipment has improved dramatically in recent decades, and some dedicated amateurs now possess spectrographs capable of measurements that would have been state-of-the-art at professional observatories 30 years ago. One amateur group in Australia reported detecting a Proxima Centauri flare independently using a 14-inch telescope, which is the astronomical equivalent of a birdwatcher spotting a rare species from their back porch, while the professionals are still setting up their field station. The global response to Webb's Alpha Centauri observations was not just scientific, it was cultural. Something about the idea that our nearest neighbour might be more complex and more alive than we thought resonated with people far beyond the astronomy community, and that resonance was about to ripple outward in ways that surprised even the scientists who started it. The ripple began with a question that is deceptively simple and philosophically bottomless. What if we are not alone, and what if the proof is right next door? You're lying on your hillside and the dew is thickened now, each blade of grass wearing a tiny bead of moisture that catches the starlight like a field of miniature lenses, and the thought settles over you the way fog settles into a valley, gradually and then all at once. The Webb data had not confirmed life on Proxima B. Nobody with any scientific credibility was claiming it had. But the methane hint, the possible atmosphere, the debris disk suggesting hidden planets around Alpha Centauri A, all of it conspired to drag the question of extraterrestrial life out of the realm of pure speculation and into the uncomfortable daylight of plausibility. And plausibility, it turns out, changes things. The first thing it changed was the Drake equation, or more precisely the way people talked about it. The Drake equation, formulated by astronomer Frank Drake in 1961, is a probabilistic framework for estimating the number of active communicative civilizations in the Milky Way. It consists of a string of factors multiplied together, including the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually arises, the fraction where life becomes intelligent, the fraction that develops detectable technology, and the average lifespan of such civilizations. When Drake first wrote it down, nearly every factor was unknown. It was less an equation and more a structured expression of ignorance, a way of organizing what we did not know into a format that clarified how much we did not know. Over the following decades, astronomers filled in some of the blanks. The rate of star formation was measured. The fraction of stars with planets, once completely unknown, was revealed by Kepler and other exoplanet missions to be astonishingly high, essentially 100% on average. But the biological factors, the ones that ask whether life actually begins on habitable worlds and whether it evolves complexity and intelligence, remained essentially unconstrained. Webb's Alpha Centauri data nudged one of those factors. If Proxima B has an atmosphere, and if that atmosphere contains methane, then even without confirming biological origin, the probability that habitable zone rocky planets can retain atmospheres around red dwarfs shifts upward. And since red dwarfs are by far the most common type of star in the galaxy, comprising roughly 70% of all stars, any adjustment to the habitability prospects of their planets has an outsized effect on the overall calculation. Before Webb, many astronomers had essentially written off red dwarf planets as hostile, atmosphere-stripped wastelands. After Webb, that pessimism looked premature. The error bars on the Drake equation did not collapse, but they shifted in a direction that made optimists feel slightly more justified, and pessimists slightly less comfortable. The philosophical implications radiated outward from there. Theologians weighed in, as they always do when the question of extraterrestrial life becomes culturally prominent. The Catholic Church, through the Vatican Observatory, had already stated decades earlier that the existence of extraterrestrial life would not contradict Catholic doctrine, a position that surprised many people who assumed the Church would be hostile to the idea. Other religious traditions offered a spectrum of responses, from enthusiastic embrace to cautious silence to outright rejection. Historians of the relationship between science and religion note that the discovery of heliocentrism, evolution, and the vast age of the universe each provoked similar cycles of theological adaptation, and scholars still argue whether each new scientific revelation ultimately strengthens or weakens religious frameworks, or simply forces them to become more sophisticated. Here is a quirky cultural footnote. Within months of the Webb Alpha Centauri findings becoming public, the real estate market for land on Proxima B briefly became a thing. An enterprising website began selling novelty deeds to parcels of land on the exoplanet, despite the fact that no international legal framework recognises property rights on celestial bodies, and no human has any means of reaching the place. The Outer Space Treaty of 1967 explicitly states that no nation can claim sovereignty over a celestial body, but the treaty says nothing about individuals selling fictional parcels for entertainment value. The website made a surprising amount of money before the novelty wore off, which tells you less about property law and more about the depth of human desire to claim a piece of whatever comes next. But beneath the jokes, and the merchandise and the philosophical debates, something more serious was happening in the scientific community. The Webb data had demonstrated that the tools now exist to begin answering the question of whether life exists beyond Earth, not in 100 years, not in 50, but within the working careers of scientists who are alive today. The methane detection on Proxima B was preliminary and ambiguous, yes. The debris disk and candidate planet around Alpha Centauri A were suggestive but unconfirmed, yes. But the fact that a single telescope, observing for a limited number of hours, could extract this much information from the nearest star system implied that the next generation of instruments, the ELT, the Habitable Worlds Observatory, future space telescopes not yet named, would be able to push much further. The question was no longer whether we could look for biosignatures on nearby exoplanets. The question was how quickly we could build the tools to do it properly, and that shift from whether to how quickly is the kind of quiet revolution that does not make the front page, but changes everything underneath it. The revolution is already underway, and it moves with the unhurried confidence of a process that knows it has momentum on its side. You are deep in your hillside now, so perfectly settled that the boundary between your body and the ground has softened, and the dew on the grass around you has turned the air into something you can almost taste, cool and mineral and green. Above you the stars continue their ancient rotation, and among them, invisible to your sleepy eyes but burning with quiet significance, Alpha Centauri holds its position in the southern sky, keeping every secret it has not yet surrendered. The next Webb observation cycle has already allocated additional time to the Alpha Centauri system. The scientific case, bolstered by the results from the first round, sailed through the time allocation committee with considerably less resistance than before. The new observations are designed to address the specific ambiguities left by the initial dataset. Longer integration times on Proxima B using MIRI will improve the thermal emission measurements and either strengthen or weaken the case for an atmosphere. Additional spectroscopic observations will target the 3.3 micron methane feature, with enough sensitivity to push the detection significance from 3 sigma toward the 5 sigma threshold required for a confirmed result. If the methane is real, the next round of data should make that clear. If it is an artifact, the additional data should reveal the instrumental or stellar variability source responsible, and allow the community to move on with appropriate disappointment and recalibrated expectations. The debris disk around Alpha Centauri A will also receive dedicated follow-up. Webb's coronagraphic modes will be employed more aggressively, blocking the starlight with greater precision to reveal fainter structures in the disk, and to search for gaps or asymmetries that could betray the gravitational influence of unseen planets. Simultaneously, the ALMA array will conduct its own independent search for the disk at sub-millimeter wavelengths, providing a cross-check that operates on completely different physical principles. If both Webb and ALMA see the disk, its existence becomes essentially certain. If they see the same gaps and edges, the case for planets becomes very strong. The candidate radial velocity signal around Alpha Centauri A will be pursued with the espresso spectrograph at the VLT, and the team has requested a dedicated multi-year monitoring campaign to build up enough data to either confirm the roughly 200-day periodicity or expose it as a stellar activity artifact. Radial velocity confirmation of exoplanets around bright binary stars is notoriously difficult, and historians of the field have noted that Alpha Centauri has humbled some of the best planet hunters in the world. Scholars still argue whether the system's resistance to clear planetary detections reflects an actual scarcity of planets, or merely the extreme technical difficulty of finding them in such a challenging observational environment. The optimistic interpretation is that planets are there but hiding. The pessimistic interpretation is that the binary gravitational environment may have prevented stable planets from forming in the first place. Webb's debris disk, with its suggestive inner edge, leans toward the optimistic camp, but leans are not confirmations. Further into the future, the Habitable Worlds Observatory, a space telescope concept currently in the planning stages at NASA, is being designed with the explicit goal of directly imaging Earth-like planets around nearby Sun-like stars and characterizing their atmospheres for biosignatures. Alpha Centauri A is near the top of every target list that has been drafted for this mission. If funded and built, the Habitable Worlds Observatory could obtain a direct spectrum of a rocky planet in the habitable zone of Alpha Centauri A, measuring its atmospheric composition with enough precision to detect oxygen, ozone, water vapour and methane simultaneously. That combination, if found in thermodynamic disequilibrium, would constitute what most astrobiologists would accept as strong evidence for biological activity. The telescope is at least a decade and a half away from launch, which sounds like a long time, but is a blink in the context of the question it is designed to answer. Here is one last quirky detail to carry with you into sleep. The photons that Webb collected from Alpha Centauri during its observation left the star system in roughly 2018. That means the light was already in transit, sailing silently through the interstellar void when the Webb telescope was still being tested on the ground in a clean room in California. The starlight and the telescope were on converging paths for years before they met. Like two strangers walking toward each other on a long road, each unaware of the other until the moment of encounter. There is something deeply lovely about that. The universe sends its messages whether or not anyone is ready to receive them. Webb happened to be ready, and what it received has changed the way humanity thinks about the house next door. And you, lying on your hillside, are part of that change. Every person who looks up and wonders is participating in the same impulse that built the telescope, that wrote the proposals, that analysed the spectra, that argued about methane and magnetic fields and debris disks. Curiosity is the thread that connects all of it, from the Aboriginal astronomers who wove Alpha Centauri into the dreaming, to the engineers who folded a golden mirror into a rocket and sent it 1,000,000 miles from home. The thread does not break. It just stretches, reaching further with each generation, and tonight it reaches all the way to you. And now, as the story folds itself closed like the petals of a flower following the sun below the horizon, you can feel the night settling fully around you. The stars are still there, every one of them, but they have softened, their light diffusing into something less insistent and more companionable. The grass beneath you is warm where your body has pressed it down and cool everywhere else, and the dew has made the air taste clean and quiet. You do not need to think about methane absorption features or debris disk dynamics or radial velocity residuals anymore. Those details are being tended by thousands of careful minds around the world, and they will still be there in the morning, patient as starlight. For now, your only responsibility is to breathe, slowly, deeply, letting each exhale carry away a little more of the day's weight. The universe next door will keep its secrets for a few more hours. Proxima Centauri is flaring softly in the dark, but you cannot see it, and that is fine. Some fires are too far away to feel. The hillside holds you, the sky holds the hillside, and somewhere out there, 4 light-years away, a small rocky planet is turning its face toward a dim red star, and whether anything on its surface is looking back at you is a question that can wait until tomorrow, or the tomorrow after that, or the one after that. There is no hurry. The stars are patient. You can be patient too. Close your eyes, let the dew settle, let the dark go soft. You are exactly where you're supposed to be.